Um, Welcome to my presentation about Gluster for system administrators. My name is Niels de Vos. I live in the Netherlands. I work for Red Hat. I am a software maintenance engineer that is part of the Red Hat Global Support Services. For my work, I solve complex customer cases, customer open support cases with Red Hat when they have issues. Mostly these customers are system administrators, and if these support cases are complex enough, they get passed on to the team where I work with. We will investigate, we will write bugs, bug fixes, patches, and we document our troubleshooting steps and proposed solutions. For the Gluster community, I am the release manager for the current stable release, that's 3.5, and I am the sub-maintainer for anything related to NFS. For that, it is my duty to review patches and merge these patches in the different Git branches. Today, I will talk about what Gluster is and how you can use it and deploy it in your environment. During the presentation, you can ask questions. I like the presentation to be interactive, so I included several demos. If you have any questions, please ask immediately. Don't hesitate and ask questions at the end. If there is little time, or if you want to propose a use case, a feature, or anything, you can find me afterwards, after the presentation, walking towards the Red Hat booth. If there's anything, the guys from Red Hat or from Fedora should know me and can probably locate me wherever I am. So if there's anything, just visit over the coming days, and I'm happy to talk to you, discuss anything Red Hat storage related or Gluster community related. GlusterFS is completely written in user space. It is a scale-out storage solution. It is a file system. It is not block storage. For example, Ceph is mainly targeting block storage. GlusterFS is targeting file systems. So it is a file system comparable to NFS or to CIFS. It is completely distributed. You can have many servers providing parts of the file system, and we offer a lot of functionality in different layers. This makes it possible to have replicated files or distributed files or a lot of other options. There is no metadata server needed for GlusterFS. It is a fully distributed file system. That means that there are no or very little scaling issues. Only if you go into many servers, you might have some scaling issues, but there's no metadata server that is the immediate bottleneck for Gluster. Probably around 100, you start getting some unusual issues. It will work, but you have to be careful. You have to approach things a little bit different. So, yeah, if one storage server has several terabytes, or maybe even petabytes, and you scale to 100 servers, you already have a lot of storage. So those deployments are very rare. Because GlusterFS is a file system, you would mount it normally in your local client systems. Any application can be used to use GlusterFS. If you use object storage like Swift or Amazon Office object storage, you have to adapt your application. This is not the case with Gluster. This is the diagram how Gluster interacts. You can mount over Fuse, which is a file system in user space. It's a user space application that provides access through the local file system. You can mount over NFS, and these clients will connect to all the storage servers directly. We have another client access model that is a library. This library can be used, for example, in Samba. Samba is the CIFS access protocol, and there is a GlusterFS plugin upstream in the Samba repository. It links to libgf API. Okay. Yep. So libgf API is the library, and you can include this library or link with this library from Samba. You load the plugin, and Samba acts as a GlusterFS client, and it can connect immediately over the GlusterFS protocol instead of going through the local file system, which has a high penalty. It adds another latency. You can use this library for your own applications. We had people from IBM that implemented a QEMU layer for Gluster. So now you can put your VM images on Gluster. QEMU speaks the Gluster protocol, and it is possible to have high performance virtual machines running on Gluster without the need for local file systems anymore. So, because I work for Red Hat and I'm part of the support organization, anything I do or work on, or most things I work on, is related to Red Hat Storage. Red Hat Storage is the enterprise version of the community GlusterFS. Customers open support cases for Red Hat Storage. If we notice that customers have the community GlusterFS version, they would need to go to the community to get support. So use the mailing list, use the IRC channels, and Red Hat cannot support the community version. So Red Hat tests GlusterFS on a certain version. It exports many patches. You get the support from that people are used to from RHEL. Somehow the next slide should pop up, but so Gluster is comparable to NAS solutions, network attached storage. It can replace your SAN in certain environments. SAN is very, very expensive, and NAS is, depending on the vendor, also very expensive. And especially if you want to scale your storage over several years, the solutions that NAS and SAN vendors offer really get expensive. Gluster runs on normal commodity hardware, and therefore any organization is allowed to use practically any hardware. This makes it much much more cost effective for organizations to implement Gluster and compared to NAS and other SAN. The common solutions that Gluster addresses is large file systems, mostly petabyte sizes. Content delivery networks is a very common use case, like MP3 vendors or video on demand. Backup, archive, and all is a very obvious example. We do a lot of integration with several backup vendors, and these backup vendors advise you to use Red Hat storage if you prefer that over a NAS or a SAN. Also, infrastructure as a service you can provide over GlusterFS, and other objects you do not want to store, for example, in the database. If you want to upload a lot of images, you have a reference in a database, but you don't want to include the image in the database, you can put the image on GlusterFS. There's also the possibility to use Hadoop. Hadoop is big data. If you're not familiar with big data, or an example from big data is if you have many servers, each server collects its own log files, and you want to search for certain error messages, how often these error messages occur on servers. What you can do, you can copy all the logs to a certain central place and do a grep for the error message, which is fairly inefficient. You would need to transfer all the logs to one central server. If it doesn't fit on this central server, you have to do it in batches, which is not very practical. Big data addresses this by moving the workload or the task to the server that contains the data. So instead of doing the grep on the central server, you would implement a little big data application, and you send this grep command to all of the servers that has the logs. These servers return the results of their grep, and the process that executed this distribution of the command receives all the results and returns the results much more quicker than doing the centralized grep. GlusterFS is one way to use big data or to provide access to big data, and Apache and Intel and Hortonworks, they all provide Hadoop implementations, and GlusterFS is able to use, or the other way around, these Hadoop implementations can use GlusterFS as a backing store for the data. We also do a lot of integration with the OpenStack people. Several components in OpenStack are already Gluster ready. So Swift, the object store, is available with GlusterFS support. In Swift, you speak about objects, about containers, and about accounts. If you map that to Gluster, you would see that an account is a volume, a container matches a directory, and an object is located in a directory and is effectively a file. For the virtual machine image storage, there's integration with Cinder and Glance, and Cinder and Glance know how to start QEMU, or how to provide QEMU, or they provide with the needed configuration to start QEMU with the libgf API bindings, so that you have high performance VM access. With Gluster, everything is modular. The main thing that Gluster has are the translators. A translator is a very small or kept as minimal as possible layer that has one certain functionality. For example, there is a layer for caching, there is a layer for logs, there is a layer for POSIX file access. Everything that is getting implemented is implemented as a translator and adds new functionality or replaces existing functionality or anything like that. The brick is the most basic storage unit part that is part of GlusterFS and is effectively a directory mounted, probably a logical volume, often formatted as XFS, and this brick is one part of your volume and the whole file system normally gets exported as part of the volume. A volume is combined out of multiple bricks. You can create a one brick volume. If you do that for your use case, you probably do not need to use Gluster because a one brick volume, you don't scale with it, you don't really add new functionality. You can either use normal NFS server or anything. But the advantage of Gluster is to be able to combine all these multiple bricks, all these single file servers, file systems on different servers and make one huge file system out of them. In Gluster we try to speak not too much about servers or nodes. We call them we try to call them peers. Node is a very common word in high performance computing. Server is a little undefined. It can be a hardware server and it can well be a client or a storage server. So we either call them peers or mostly storage servers. On these storage servers there are the file systems, and these file systems are exported by several processes. The brick, yeah. Yep. I'll get to that later. I'll give you an example of what the translators do and what kind of translator stack you will get. Yep. So a brick is located on a disk, logical volume, and is effectively a file system. So we advise people to use direct attached storage and not use a SAN or a NAS because that often defeats the purpose of Gluster. Gluster wants to run on commodity hardware with systems on disks that are directly attached to the server. That is also what Red Hat tests, and Red Hat QA does not test or not a lot test bricks that are stored on a network file system or on a SAN. If you approach Gluster, you normally should approach it as a dedicated storage server. It is not a Linux server. Well, it is a Linux server, but it is not a normal Linux server. If you use the files that are located on the bricks, then you can run into issues. So any junior system administrator should be kept away, possibly from the storage servers, and only the people that know about how Gluster works, they should be accessing the storage servers. The others should be very careful. So everything else works as a normal Linux server, but storage is definitely something that is a little bit different than normal things. Scaling is very important. You want to, so if you gather a lot of data. Over the years, you gather some. You start with some gigabytes. After that, you make more pictures and more pictures. You make some videos, and you will get several terabytes, possibly even petabytes. You do not know how much data you will have in advance. It is very difficult to plan storage in advance. So scaling up and scaling out is what Gluster is all about. It needs to be able to add more disks on the storage servers. You add more file systems, and if your file systems or your file servers are full of disks, you cannot add any more disks. You just add more servers. So scale up is like adding more disks to your server. You have your RAID cabinet. If you have a cabinet that fits 60 disks, you start maybe with 12 disks, so you can expand a couple of times. You have a second server for your application, so that you don't lose data if one of those servers is down. And if both of these servers have 60 disks, you have to scale out. You have to add more servers, and that's what Gluster makes possible for you. Any questions about scaling up, scaling out? We have, with Gluster, we have a way to distribute files. Distributing files over different file systems is done by a hash. So every client knows where the other, or where the file is located or should be located. It hashes the file name, and this hash is located to a brick. A brick has a directory, and this directory has a hash range. And if you have two bricks, in this case of the diagram, you have export 1 and export 2. Export 1 has the first half of the hash range. Export 2 has the second half of the hash range. If a client accesses a file, it knows the algorithm to create a hash, a hash for the file name. This hash is either located in the range of export 1 or export 2, and the client knows immediately where to find the file. I can show you a little demonstration about how this is done. So creating a brick, I've scripted it so that I don't have to type too much. It does a logical volume create, in this case in the volume group bricks. It creates a file system on the brick, and it tries to create a mount point. Obviously forgot to create it. So now I got a brick, and it's running on my laptop, so I got a brick of 500 megabytes. It's got, yeah, easy as that. Now I got a one brick system, which is not very interesting. It's normal storage. So the second step would be to create a volume. So I'm currently on storage server 1, and I create a volume using the brick Fisl A, and it's one command to create the volume, Gluster volume create, one command to start the volume, Gluster volume start, and the last lines show the details of the volume with Gluster volume info. This is a one brick volume, but this is not very interesting. So what we want to do is we want to make a replicated or a distributed volume. So this was the distributed volume. My server is called server 1, storage 1. The brick is not export 1, but bricks slash Fisl A slash data. And I got a storage server 2 as well. So what this does is it calls Gluster pair probe. Gluster pair probe is a command to add another server to your trusted pool. So now we have a so-called Gluster cluster with 2 systems. It's running on localhost, and we have a storage hostname number 2 as well. We have added a brick. It failed to do the rebalance, but that's my mistake. Doesn't really affect us here. We added another brick, and we see now that the Gluster volume info shows 2 different bricks. 1 brick on storage 1 and 1 brick on storage 2. And now we have a distributed volume. We have the volume name Fisl, and it's marked as distributed. It started, so this new brick was added while the volume was online, and any system using this volume should not have any issues. It just notices the file system suddenly grew by twice the size. The common use is also with a replicated volume. This is similar to a RAID 1, but on file level. So that means that if a file is created on 1 brick and it is replicated, then the file is also immediately created on a 2nd brick. So if one of those bricks goes down, you still have a copy of the file. Obviously, just replicate it and just distribute don't really help in the most use cases. We want to have a combination of both. We want to distribute, making the scale out possible, but we also want the security of duplicate files. So what we do is we create a distribute replicated volume, which means that a client will write to 2 of those bricks. Those bricks are located on different storage servers, and you can have multiple file systems for load distribution, or you can add many more storage servers. In this case, we have 4 storage servers. That's not something my laptop likes too much, so I'm doing it with 2 storage servers. In this case, what I'm executing is the Gluster volume add brick, and I say I want a replica 2. You could say replica 3, replica 4 if you want 4 copies. Replica 2 is normally sufficient and most cost effective. You pass new bricks on the command line, and that's it. It's as simple as that. Any questions so far? Yeah? No, so I got 2 servers. I got a storage server 1 and a storage server 2, and I run it only on one system. I have to create those bricks, so the logical volumes and the file system, and I have to mount the file system on all of the storage servers. That's not an automated thing, at least not with the command line. But the adding of the new bricks to the volume only needs to be done on one system, and it passes this new configuration of the volume on to all the other servers in the trusted pool. So, yeah. the data access, because what we've done now is we've created a volume, but we're not using it. The data access can be done over the Gluster FS native client, which is implemented in Fuse. It is available for Linux, it is available for NetBSD, and since very recently there is a major effort ongoing to make this available for macOS. So people can use the native connection through Fuse and mount the volumes. You can access the volumes over NFS. NFS v3 is built in Gluster, and volumes are by default enabled over NFS, so anyone can mount, any operating system that can mount NFS can use the volumes. There is the Samba plugin I mentioned earlier. It is possible to configure Samba to export these volumes, and you can access your data on your Windows workstations. So mounting the volume is really easy. You have to install the Gluster FS Fuse RPM in case of Fedora or RHEL, and I think there's a Gluster FS Fuse package for Ubuntu. The command is just mount-t Gluster FS and then the hostname, colon, name of the volume, and the mount point. So it's very similar to NFS. You just replace NFS with Gluster FS. You can mount the volume from any storage server. So it doesn't matter if I would write, in this case, localhost or storage 2. It just needs the name of a server that contains the volume configuration, and the client does the rest for you. Gluster for OpenStack is now called, since a couple of weeks, Swift on File. So that's the extension that the Gluster developers for OpenStack Swift are writing. It was called Gluster for OpenStack before, and before that it was called Unified File and Object Access. It is very confusing, and they like to change names. I don't know how long they will take, how long they will stick with this current name. But if you ask in the Gluster community, or if you go to the website, you should be able to find the current name and the components that you need. The latest edition that is made available in the release candidate for NFS Canisha is that there's now a module in NFS Canisha that implements usage through the libgf API. NFS Canisha is a user space NFS server. Gluster contains its own NFS server implementation limited to NFS version 3. NFS Canisha is more advanced. It supports NFS version 4, and it will also support PNFS, so that's NFS 4.1. And we're slowly moving to using NFS Canisha instead of the Gluster internal NFS server. Mounting over Fuse involves the Fuse kernel module. There is a lot of interaction between the file system going through Fuse, going over the network, so it's not always very performant. It is the easiest way to access your volume. For a lot of environments it is sufficiently fast enough. The NFS or the Fuse client has automatic failover, so it knows how to talk to each of those storage servers, well, to each of those bricks in fact. If one of those bricks is not working for whatever reason, maybe a network outage, maybe a disk failure, the Fuse client will automatically fail over to other bricks. NFS is a little bit different. NFS is actually a Gluster FS client as well, running on all of the storage servers. But when a NFS client accesses the NFS server, it will go through a particular storage server. It will always pick this server unless you do round-robin DNS for load balancing or something similar like that. So the NFS server is, so instead of the NFS client contacting all of the bricks, the NFS server is contacting all the bricks, and yeah, there's a bit different use case for it. With the previous release of Gluster FS, we introduced libgf API. libgf API provides support for your applications, and this makes it possible to circumvent the Fuse layer. The Fuse layer has a lot of context switches with the kernel, and those are very latency sensitive. So going through a library makes a lot of sense for example, QEMU with virtual machines, or for Samba, if you do a lot of I/O through Samba, that definitely helps a lot too. The rest of the stack is always kept the same. So the list of translators is the same for Fuse, for NFS, or for libgf API. In the latest version of Samba, the latest version is Samba 4. Something. We introduced libgf API with Samba, and Samba takes the advantage, and we have reports of performance improvement for over 200%. So with libgf API, we're definitely on track of improving performance and providing better use cases for different situations like Windows systems. Gluster contains several components. The main component is the Gluster D management daemon. This management daemon is, before I started my demonstration, it was the only daemon running on the storage server. It is responsible for receiving the commands from the command line interface and handling those commands, for example, by creating a configuration file for the volume and adding bricks to the volume. It speaks to other storage servers. When you do a Gluster peer probe, it also pings storage servers every now and then. The Gluster FSD is the Gluster file system daemon. It is a process that is exporting one brick. So if you have many bricks on your storage server, you would see many Gluster FSD processes. These Gluster FSD processes are started by Gluster D when the server starts up, or when you add new bricks. The Gluster FS command or binary is the client side. The Fuse client is a Gluster FS process. The NFS server, because it is a client, is also a Gluster FS process. Only libgf API doesn't start Gluster FS because it's a thread in the library itself. The script to mount Gluster FS over Fuse is mount.glusterfs, and it's just the helper script, just like mount.nfs and other mount helpers that speak to the mount binary itself. The Gluster command line interface, there's a Gluster CLI command that I use to execute all the commands, is a very small binary. It talks to the Gluster D process and doesn't contain a lot of intelligence itself. It just says, okay, I want to peer probe another storage server, I want to add a brick to this volume, and the cluster D management process is actually executing this. So back to the translators. The left side is what a brick process contains. The right side is what a client process contains. The bottom side on the left, you see storage POSIX. That is one translator that knows how to speak file system. So it uses open, it uses read, write, system calls. There is an access control. There are many other layers. Each have their own specific functionality. The protocol server on top of the left side is where the protocol implementation is done. So GlusterFS is a protocol based on SunRPC. It is very similar to NFS, at least for the format. This protocol on the left top side speaks to the protocol on the right bottom side, and the right side is the client. It contains several optimizations client side, like caching, read behind, and so on. And the upper level, the upper right block, is either the NFS server, the Fuse client, or libgf API. Any questions to this diagram? So, in order to show you what is seen in practice, all the configuration is stored on the varlib cluster. I've created one volume, and the configuration contains already quite some files. So there's one. So the .vol files are the is the configuration file for each of the processes. So there is a Fisl Fuse .vol file, and this .vol file is passed on to any Fuse clients. The bricks have their own volume file. And this is how a list of translators looks like. Remember that storage POSIX on the top here was the blue one on the bottom, the green one on the bottom, on the left side, and that is the file system API. And we just tell the POSIX translator an ID for the volume, which is unique for the whole volume, and which brick it is going to use. So is the whole list of translators available, and the last one is the protocol server, where the network access is done. This is what the client receives. So protocol client is the bottom side of the right translator stack, and the protocol client receives the RPC from the protocol server part. DHT, the second translator, is the distribute functionality. The first translator here is the replication. So if the client does something, it goes from bottom to top, meaning it goes it hits the right behind, it hits the distribute, and distribute says I got two sub-volumes. A sub-volume replicates 0, replicates 1. And these two sub-volumes are listed here. Replicate says, okay, I got a sub-volume on the top one on 0 and 1. The other one is 3. And together this builds the whole storage stack. So it says, okay, which brick is client 3, it is hosted on storage 2, and the brick directory. So this is how how the whole configuration is built and put together. Any questions for this? So Gluster is included in Fedora. It is included in the Red Hat storage product for Red Hat customers, and Amazon provides an AMI image that also includes GlusterFS. You can go upstream. Upstream provides RPM packages. We have a community member that provides Ubuntu packages. It is also included in Debian, although the current stable Debian has a relatively old GlusterFS version, but it's Debian stable, so we're all used to that. With this, I'm done. These are some references. You can find the slides on my page. If you have any questions or if you want to see any demos, let me know. Talk to me, find me, send me an email, and I'm happy to help you out. Yep. So I will also be presenting on Saturday morning at 11. I will provide a talk about debugging GlusterFS with Wireshark and SystemTap. So my major duty at Red Hat is fix bugs related to Gluster and NFS. So Wireshark and SystemTap are my major tools that I use to debug. And on Saturday, I will show some use cases and some problems that I was working on, and the way how to debug relatively complex issues. No questions? Thank you.